Hello everyone, welcome back to our YouTube channel, Becoming a ROS Developer. Today we've got Ying, who has completed the course ROS 2 Basics with Python, and he will be giving a presentation on the work he has done, and he will get into the details about how he managed to get the task accomplished. We'll first of all see a demonstration of his code base working on the real robot, and then we'll get into the details. Finally, we will then finish by asking a couple of questions to get some more information on how he did it. So I will now hand over the floor to him so that we can begin. All right, hello Ying. You can
Hello.
begin presenting, and we'll
Okay.
get into the details.
Okay. Hello everyone. Okay, I will open my slides. All right. Hello everyone. My name is Ying, and today I'm going to do the slides, presentation about the wall following, and past recording of the Turtlebot based on the laser and odometry. And first part, this is my short introduction of me. My name is Yuhang Ying, a PhD student in chemical engineering at the University of Houston. And I'm currently specializing in nonlinear dynamic and linear-based control method, and I have very interesting previous experiences in robotics. So if you are interested and would like to make some comments, I would be very it would be very good. I'd be very grateful. All right. So let's come to the main point. Okay, let's see the overview of the goal of the ROS check. There are mainly three sections of task. The first is wall following and wall founder, the odometry action, which
Hello
is
Ying.
used to record the hello.
Sorry to stop you there. If you're connected to the real robot already, can you show us a demonstration of your code base working, and then you can get into the slides afterwards.
Okay. Oh, okay.
So maybe you can
Okay.
terminate and then start again and explain as you go.
Okay. Wow. Okay, this is my project, and uh, I'd like to make it into a good position. Go back to its starting point, and currently, uh, let's come to the okay, and let's see if it works.
All right.
Okay, you can see let's start the action, the server, and let's start everything out again. This is server, wall founder. Okay, okay, let's get started. As you can see, the wall following node has sent a request to the wall founder server, and it now begins to head to the nearest wall and approach to it to the 0.3 meters. And after which, it will make it at the right side of the robots, and you can see that so far everything has goes well. All right, and also after it begins moving forward. This odometry will begin recording the total distance traveled, and when it reaches the corner, it should start diverting. And as
Okay.
you can see, everything works well, right?
Mm-hmm.
And you can see that this is currently working. And let's wait a little bit until it finish the whole circle. All right.
All right.
Yes. Oh, oh, sorry. This is so
it's,
embarrassing.
it's now okay. Try to follow the wall one more time.
Yeah, this is okay. This works. Normally this works, but I don't know why today some real robots.
Yeah,
I
there
don't
is
know why. All
always
right.
a situation where it doesn't behave as you expect,
Yes.
right? So let's get it going again and see how it behaves.
Yes. Yes. This is weird. Okay. Yes. I prefer to start them separately. Although we can start all, but
Okay,
if we start all, the information will be mixed, and it's hard to see what's going on.
I
All
see.
right.
I see. Normally, you must have
Okay.
one, let's say, your service after it has found the wall, then it must now hand over control to the wall follower, and then the wall follower must also hand over control to the odometry, right? If you do that right,
Yeah,
then
yeah,
you
yeah.
don't have problems by having to start everything in one launch file.
Yes. Yeah.
All right, let's see how it goes now.
Mm-hmm. Oh,
It happened
this
again.
is
All
okay.
right. Don't worry
Okay.
about it. Let's get into your presentation, and then you can explain to us why you think this is happening, and also the process you went through to get it to at least follow the whole part that the section that it managed to follow.
Okay. Yes. But I think I can make it. Let's give it another try.
All
I
right.
think I know what is happening. All right.
All right.
I know what is
We've got
happening.
15 more minutes, so your time. Let's go for it.
Okay. Okay. Let's just start it right here. All right. Don't go to the original position. I think it's the same.
Mm-hmm.
Okay. Okay. Maybe I can show you a successful case in my presentation I have recorded before. All right.
That'll be good. Also, that'll be good. Let's just let this third and final try finish, and then we can do that later.
Okay. Okay. Oh wow. This time it seems it looks good, better than before, right?
Let's see.
Oh, still not good.
It's
Oh, I think there's some.
obstacles.
Okay,
Yes.
okay, let's come to the presentation part, all right?
All right.
This is so embarrassing. Okay, I think there are three tasks of the project, and there are also some challenges for the wall following behaviors. You have to obtain the correct right distance in real time, and you sometimes your right laser may not point straight to the wall, and it may a little bit greater than the true value. So you have to rectify it. And also you have to make the motion smooth and accurate, especially diverting. And to address this issue, I use the odometry to record the current pose of the robot. And for the wall founder server, how to recognize the nearest wall and how to make sure the approach wall is right at the outside of the robot is also very difficult. And sometimes, by on the instructions of the textbook,
Mm.
it told us to treat the nearest obstacle as the wall, but I think that's not good because when you are close to an object and you recognize that as a wall, that would be awful, right?
Mm.
So later I will introduce how I did this in my method.
All
And
right.
for the automated action, it is rather easier. It just asks us to begin the recording and accumulate the total travel distance. All
Yes.
right. Okay, and let's see the overview of the robot. The Turtlebot robot is driven according to message type twist, and we can control the linear velocity and the angular velocity by publishing to the topic. And there are also a little bit difference between the real robot and simulation. And the
Mm.
first is the laser configuration. It's in the you can see that the first the laser is at the front of the simulation, but for the real one,
Mm.
it is at the back side
Okay.
in the first. And also, if you hope your command to find the real robots well, you have to make sure your control your the frequency of sending the command is controlled. Otherwise, it will lose something. And this has cost me a lot of trouble until I found it,
Mm-hmm.
right? And also, it has a safe limitation of the velocity. Okay, and this is the overview of the code set of my code setup. You can see that there are totally three topics that I use to control the robot, and the command, one is used to command the velocity, and the laser scanning, and the odometry. And
Mm-hmm.
I subscribed it to both the laser scan and the odometry to make my wall following behavior smooth. But well, it turns out to be not robust enough. All
I
right,
see.
that's really a pity. And also for the action node, I only subscribe to the odometry because this is rather easier, right? All
Oh,
right.
okay.
And for the wall founder node, I subscribe to laser and the odometry.
Mm-hmm.
And okay, let's see our workflow. As the wall founder is the first behavior of the robot, so let's introduce it first. And instead of using the nearest object as a wall, I use the root mean square error of a range of the laser values to judge whether it is wall. As
Okay.
you can see in the figure, if this is an obstacle but it's still near, you don't want it to be a wall, right?
Right.
So by using the root mean square error of the laser,
Mm-hmm.
and when the root mean square error is converged to a small value, you can judge it as a wall, just like this.
All
And
right.
let's
All
see
right.
how it works. And you can see that when it is pointing at an obstacle, the root mean square error is like large, it's 0.6, all right?
Mm-hmm.
And when it close to a wall, the root mean square error reduced to 0.01, and this is very accurate, all right?
Mm-hmm.
And this will be judged as a wall. And then it will finish the wall founding behavior, right?
Okay.
So this is my wall founder. And let's see the wall following. The at the very beginning of the wall founding behavior, it will send a request to the wall founder to make it begin the wall founding behavior.
Mm-hmm.
And when the wall is found, it will also send a request by using its client to the odometry action server, and after which it will walk into its while loop, do a server control of its of its distance to the right wall and its direction it will consistently rectify its direction by using the odometry, and we use the yaw pulse of the odometry.
Okay.
And
Okay.
when it is close to a forward wall, uh, we will augment the reference yaw pulse by half pi to make sure we make a smooth and accurate diverting, all right?
Okay.
And I and we will send a large angular velocity and a relatively smaller linear velocity, and until the real yaw pulse is close to the reference yaw pulse,
Okay.
and this will stop diverting. And
Okay.
the workflow of the action server is rather easier, as it only realizes uh, the past recording behavior, and we only uses the odometry topic. But to better illustrate the performance of our robots, as you can see in the last part, in the final end, I also added output of the trajectory point PNG
Mm-hmm.
to better evaluate our behavior of the wall farming. All right.
All right.
Okay. And let's comes to our simulation results. And as you can see, in the simulation, I think everything works good. You can see it finds a wall and do the wall following behavior. This is very smooth, very accurate. I hope this also happens in my presentation, but
Right.
this is so embarrassing. And you can see the trajectory is also very good. All right,
All right.
this is just what we want. And for the real robot results, this is I recorded this a week ago, but I don't know why today it doesn't work. But let's see anyway.
Okay.
And now it's finding the wall and make it to the right side of the robot. And I also recorded the value of some state, but maybe this is not clear, right?
All right.
Mm. And as you can see, everything works well.
This is where it was failing, right? On the second corner.
Yeah, 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 yeah,
Yeah.
yeah. Mm. Wow. I think I know why this may happen, why that this phenomenon happens. I can fix it. Well,
Why do you think it failed then today? What is it that
uh,
you presume you have realized?
because I was I was using the odometry value, the yaw value by
Yeah, I
using
was.
the MU.
Yes, I was gonna go there
Yeah,
too. The fact that you used it to guide it on whether it's
yeah, yeah.
close to the wall or not, right? It's just an assumption. I was gonna mention that earlier, but yeah, it's good that you it comes to your mind as well. But yeah, go ahead. What have you been? What part of that specifically?
I think that is the when the value go past the pi, it will suddenly go back to the minus pi, right? I
Right,
think I didn't process that
that
well.
sudden
I
change.
just Yeah, yeah. That I think I didn't process that sudden change well. And when it is heading to a very close value to where it may change suddenly,
Right,
I didn't consider that.
right,
And sometimes it works because I was lucky enough it doesn't happen. The sudden change doesn't happen.
right.
But and I think that's why I failed to do that. But you see, I think previously it works well and it works like a perfect trajectory.
Mm-hmm.
All
So,
right.
do you think if you manage to, it will probably be difficult, but if you manage to read your laser scan data, not from minus
Mm-hmm.
pi to pi, but you have it, let's say you take it as going beyond pi, right? So it will just keep counting, and you use the range of 0 to 360 despite whether it occurs between 720 and the next number. Do you think that would have smoothened it out, or that would have eliminated the jump from the positive to the negative?
Uh, Pardon? I didn't
So
get it.
my
Sorry.
yeah, it's fine. My question was, do you think if you could for some reason manage to get it to keep counting, right, so that it doesn't skip from I'm going to refer to degrees here, so that it doesn't skip from 180 to minus 180. If you could keep it counting further so that it goes 180, 190, or 181, 182,
Oh,
if it could keep doing that, do you think you wouldn't run into this problem?
I think I can resolve these problems once and for all. I will not run into this problem again
Right.
if I add a additional process for this problem.
All right, all
I
right. If
think
you
this will
add
not
an
happen
additional
again.
handling section for when
Yeah,
this
yeah, yeah,
special case
yeah.
occurs, okay, that's quite good. It's quite good line of thought there. Anyway, let's go ahead.
Okay. This is my final part. Okay. This is my final part of the presentation, and I learned a lot
All right,
in this course. Yes.
all right. So that's all on your presentation. Okay, just in time. Okay, fine. I'm gonna. I have a couple of questions I would like you to clarify for me. So you spoke
Mm-hmm.
about the frequency of sending commands, right? Can you elaborate more on that? What do you really mean when you say that you had some frequencies that were difficult for for the robot to handle? Right? What frequencies were those, and
Okay.
what command or what data were you passing on the topic services or whatever?
Okay. I was trying to referring to the when we are publishing the velocity to our robot,
Mm-hmm.
and as you can see on my screen sharing, this is my code.
Mm-hmm.
All right. And when we are publishing velocity, it's just this line. When we are publishing our command of velocity to our real robot, for the simulated robot, you can pass all the commands. to
Mm-hmm.
your robots.
Mm-hmm. Mm-hmm.
Your commands will always fund your robots well because it works in let's see, simulated time step. So
Right,
every
right.
time you send a command, the robot will receive it. It is good when we do simulation. But for the real robot, if you are sending it too much frequently, like more than 1,000 hertz,
Mm-hmm. I see, I see.
some commands will be missed, and
Right, right.
sometimes we just said once, and it will if it disappears, the 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 whole program will collapse. All right.
All right. I see, I see. Very,
Yes.
very well done. Very good explanation there. All right. I
Yes.
think we'll wrap it up here, and I'd like to say congratulations. Very nice presentation that you've done right there, Ying. So to wrap it up here,
Okay.
and
Thank
then we
you.
can finish our conversation on the meeting. So to everyone who would like to have a try and on the courses that we offer certifications on, we highly encourage you and would like to say congratulations to Ying on such a very nice presentation. Until next time, keep pushing your ROS learning.